The ratio test is a good test for series if the series has factorials involved. And so let me talk about factorials just a little bit, because those may be something you haven't dealt with just a whole lot. All right, so when I mean factorial, what I mean is, well, the notation for it, this is called 5 factorial. The little exclamation point there is called the factorial. Seen that before? Okay. What does it mean? 5 factorial. Well, the way I talk about it or explain it is, it's a countdown product. You start at 5 and then you count all the way down to 1, right? So it's 5 times 4 times 3 times 2 times 1. And of course, if it's a number, yeah, you can evaluate it. Just multiply those numbers out. I believe that one is 120. Is that right? Okay. So it is, if it's a number, factorial, you can evaluate it. So it's whatever the number is you start with and count down from there. And they get quite large quite fast. You know, you have your calculator, you can use that button on your calculator if you need to, like 10 factorial, that's quite a lot to type in, right? But calculator do that for you. Just to know what that was, but I forgot right at the moment. So 10, and then it's usually under like the probability. 10 factorial, yeah, it's 3628800. 3 minutes, a little over 3. All right, but in our practice, in our problems, what we will come across is more like an n factorial. And of course it does mean the same thing, but one thing to understand is how we can write it out. I mean, it would be n times, and then you'd go 1 less, n minus 1, right? And then the next one would be n minus 2. So if I needed to go down from n, that's the way I could do it, and then ultimately we wind up with 3, 2, 1. Those depending on how large n is, right? Now, that's fine, and we may have to do that at some point, but here's something else we might come across, that is n plus 1 factorial. And what we would need to understand there is n plus 1, of course, starts at n plus 1, and then counts down from there. What would be the one following n plus 1? The number following n plus 1? It'd be n, yeah. It'd be n, and then n minus 1, and then blah, 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 till you get to 3, 2, 1, all the way to the end there. So understand that, but what is even better to understand here is what have I got right here after the n plus 1? Isn't n plus 1 factorial n plus 1 times, and what is this? That's n factorial, okay. And so that's one of the bigger things to understand here. Yeah, n plus 1 factorial is n plus 1 times the n factorial. Okay. So what would n plus 2 factorial be? Well, I guess however you need to write it, but if we wanted to get down to n factorial, what would we have to do? We'd start with n plus 2, and then 1 less would be n plus 1, and then after that it would be the n factorial, wouldn't it? So anyway, if you can understand how we got that, then that goes a long way to helping you on these ratio test problems. Okay. So what is the ratio? Here's the ratio test. there are three parts to it. Number one, a letter I, we use I instead of ones and twos. So I is if the limit as n goes to infinity of, scroll over just a little bit so I can get this all in. If the limit as n goes to infinity of the absolute value of n plus 1 over a sub n. So you're just looking at a limit again. The limit of the absolute values is the n plus 1 term divided by the nth term. If that's less than 1, then the series, just use the a sub n series in general, is absolutely convergent. So it gives us that stronger convergence. We call it absolute convergence. We are looking at the absolute value of some things, so makes sense. But we'll talk about what this comes out looking like, the a sub n plus 1 term and the a sub n here in a minute. But let me just state it here up front. All right, so then number 2, if the limit as n goes to infinity of a sub n plus 1 over a sub n. So it's the same limit that we're looking at. If that turns out that's greater than 1, or infinity, or equal to infinity, then series diverges. Didn't quite get all the verbiage in there, but so if that limit is greater than 1 or equal to infinity, which I guess technically infinity is greater than 1, but this is the way they state it. All right, so there's one other option here that could happen. We got less than 1, we got greater than 1, or infinity. Could be equal to 1, right? So what do we got there? So 3, if the limit n goes to infinity of the absolute value of a sub n plus 1 over a sub n equals 1, well, then the test is inconclusive. You have to use something else to determine whether it converges or diverges. It still could converge, it still could diverge. This test just doesn't provide the information to tell you that. Okay? And so that's what the ratio test is. All right, so let's look at a couple of examples using this ratio test. Like I said, a lot of them involve a factorial of some sort, just like this one. So the series is n factorial over 3 to the n. It's got the factorial, so ratio test will probably come in handy. So in the ratio test, while we're looking at it, it all hinges on this this limit, doesn't it? Limit as n goes to infinity of a sub n plus 1 over a sub n, absolute value. Well, what does that mean? Well, in this case, it means the a sub n plus 1 term is just taking and plugging in n plus 1 for n there. So it'd be n plus 1 factorial over 3 to the n plus 1. That's what a sub n plus 1 is, the absolute value. And of course, a sub n, this is a sub n. I should have really denoted that, but yeah, the a sub n is, it's the defining expression there. So divided by a sub n would be divided by that in factorial over 3 to the n. That's the limit that I want to do. All right, so yeah, a lot of times this is how it's going to look. We'll have a fraction over a fraction, a complex fraction we call it. And so usually what it'll amount to is, this means divide by this. I'll write it out once here so we can see. I think we've come across things like this before, but yeah, this line here means divide, but really in practice what we're going to do is the reciprocal, multiply by the reciprocal of that. So that happens a lot. I don't usually write divide that. I usually just say times the reciprocal of that. So we're just going to flip those things over. And there's some other things we can do. Writing out step by step here first time. Okay? All right, so divide by that means times reciprocal. Well, what happens here is, yeah, that's where our previous discussion about that factorial, notice here I've got n plus 1 factorial, and then I have an n factorial, so writing that as n plus 1 times n factorial, we'll get some cancellation there. Kind of the same thing here, 3 to the n plus 1 is 3 to the n times 3 to the first. That's, kind of breaking it up like we don't normally do, but we can do that. And that's because, as you can see there, we got the 3 to the n, so there's lots of canceling that we can do here if I break those up like we said. N plus 1 factorial is n plus 1 times n factorial. 3 to the n plus 1 is 3 to the n times 3 to the first. Cancellation happens, yes. N factorials cancels, the 3 to the n cancels, and it'll wind up with a limit as n goes to infinity of the absolute value of n plus 1 divided by 3. Well, this is now to the point where we can evaluate this. Nothing really to, usually when we have these n to infinity, we divide by the largest power of whatever in the denominator. Well, we don't really have anything other than just 3 in the denominator, so yeah, this is just, think about infinity plus 1 divided by 3, that's infinity, isn't it? It turns into infinity. And so what I have here is part 2, isn't it? I've got this limit of this ratio of the term, n plus 1 term over n term, is infinity, and so that tells me overall that my original series diverges, which was n factorial to the 3 to the n, that diverges. Okay? So it's all about calculating that ratio. All right? So if it's less than 1, it's convergent, absolutely convergent. Greater than 1, or infinity, divergent. So I'm sure you remember that, right? All right, let's try another. So this one's going to be the series -1 to the n times n factorial over 2n plus 1 factorial. We'll talk about that. So let's think about our ratio here. Limit as n goes to infinity of the n plus 1 term over the nth term. Yeah. So we've got the limit as n goes to infinity. All right, so the n plus 1 term. Negative 1 to the n plus 1 times n plus 1 factorial divided by, now, here's, got to be careful. We've got 2n plus 1 factorial to start with. So if I plug in an n plus 1 there, I have 2n plus 1 factorial, don't I? When I plug in an n plus 1 for that n right there. So what I've got here is 2n plus 2 plus another 1. So don't I have 2n plus 3 factorial? That's what I get when I plug in n plus 1 here. So got to be careful there. It looks like it should be 2n plus 2 factorial, but it's actually 2n plus 3 factorial when you work it all out. All right, then I'm going to divide by the a sub n, so it's just that. Okay. Now the next thing here, let's talk about, it didn't come up any at all on our previous discussion, but this is absolute value. And so just like before, if I've got an absolute value, you know, these are saying, well, there's going to be some negative signs and alternating signs, that sort of thing involved. However, since I'm doing the absolute value, everything turns positive, right? So essentially, the absolute value here wipes out our alternating signs, the negative 1 to the nth and negative 1 to the n plus 1. I mean, we can combine those and get some cancellation there, but those are just going to be wiped out because it's absolute value. It's changing all the terms to positive. All these terms, if you will, of this limit are going to be positive. That didn't come up over here because we didn't have any alternating signs. But the negative 1 to the powers, n powers, you can just wipe those out because of the absolute value there. All right. Now, again, without going through it again, divide by this means multiply by the reciprocal. 2n plus 1 factorial over n factorial. So multiplying by that reciprocal. And then again, to save some steps, I'm going to write all this out every time. Again, on top then I'll have n plus 1 factorial, but since I've got n factorial there, let's rewrite that as n plus 1 times n factorial. What about 2n plus 3 factorial? How should I write that in light of what I've got over there on the right? Well, wouldn't 2n plus 3 factorial be 2n plus 3? Then the term below that would be 2n plus 2. And then after that would be 2n plus 1. But it's 2n plus 1 factorial, right? It's the countdown after that. So what I would have left after that is 2n plus 1 factorial. And that's going to go rather nicely with the 2n plus 1 factorial over there on the right. With me? Yes? So let's cancel. In factorials cancel. Leaves me with, let's write it all out, n plus 1 on top, 2n plus 3 times 2n plus 2. And there's, you know, several ways we could go at this one, but to follow procedures we previously talked about. Let's go ahead and multiply these out. And get limit as n goes to infinity. So we've got n plus 1 over 4n squared. Be 4n and 6n, I believe that's 10n. And then 3 times 2 is 6. Just pull that out. Not that big a deal. Yeah, so now it's looks like the infinity limits we've been always used to. One way to show this, what this goes to, is divide by the largest power in the denominator, which is n squared, and so limit as n goes to infinity would be 1 over n plus 1 over n squared, 4 plus 10 over n, 6 over n squared. We're going to divide all those by n squared. Yeah, so top goes to 0 plus 0, bottom goes to 4 plus 0 plus 0, right? Which is 0. So now we decide what that means. Well, every test has its own thing, so having 0 there, what does that mean? Well, remember back, if it was less than 1, absolutely convergent. So our series, alternating series here, -1 to the n times n factorial over 2n plus 1 factorial. That series absolutely converges. Question? All right. Try one more like that, and then we'll talk about the other test. Okay? All right, here's another. -2 to the nth over n cubed. See what happens on this. I would probably guess, because of what we're well, so let's look at the limit as n goes to infinity, a sub n plus 1 over a sub n. All right, so that would be the limit as n goes to infinity of -2, absolute value of -2 to the n plus 1 divided by n plus 1 cubed divide by a sub n, which means multiply by the reciprocal. So let's just go ahead and want to do that. So I divide by a sub n, which means I'm going to multiply by its reciprocal. So go ahead. Makes it a little easier to write there. Well, one thing we can take care of here is, again, because of the absolute value, I've got some negative things and it's going to be alternating, but since it's absolute value, get rid of the alternating signs, which in this case it's inside here, but so it'll just be 2 to the n plus 1 2 to the n. And really, I'm leaving in the absolute values because in the next unit, we'll have to leave in the absolute values throughout. I guess that's why I'm doing it here. But there's not going to be, once we get rid of those alternating signs, there's not going to be any negative terms. So we could technically get rid of the absolute value, but it's a good practice to leave those in because of what we'll have to deal with in the next unit. But technically we could take those out at this point altogether, the absolute values. All right, now what happens here is, of course, 2 to the n times 2 to the first, split that up. Show you this one. All right, so the 2 to the n's do cancel. In this case here, I don't think, yeah, it wasn't, we haven't had one where it was quite like this, but I could, you know, like before, I could go ahead and cube that out. But let me show you this other little technique when I have one like I have right here. What I can say here is this is 2, and then these two things, n cubed divided by n plus 1 cubed, I can write those as 1 cube I've got, I mean, I don't think I could have done it. Yeah, that one over there wouldn't have worked, but and that can save you from having to multiply binomials out like that. Now it's just, you know, divide this by n and that by n, and you get the limit as n goes to infinity of 2 times 1 over 1 plus 1 over n, third, which as n goes to infinity, what have we got? 2 times 1 over 1 plus 0 cubed, which is 2 times 1, isn't it? 2 times 1 cubed? It's 2. All right, so what does that mean for this ratio test? Ratio. It's great if it's 2, it's compared to 1, isn't it? That's greater than 1. And anytime you have greater than 1, diverges. So our series there diverges. Ratio test. Okay? All right, so I did want to show you one where you can use that that technique. Usually there's lots of ways to get them, different ways. But any questions on that? All right. Got one more test here to show you. It's a root test. And it's, again, for this one, it's, a lot of times it's obvious what, when you want to use it. Here it is. It's similar. It's got 3 parts, like the ratio test. Number 1. If the limit as n goes to infinity of the nth root of the absolute value of a sub n. So you're going to take the nth root of your a sub n term, well, the absolute value of the a sub n term. And if it's less than 1, then the series absolutely converges. Number 2, if that same limit, n goes to infinity of the nth root of the absolute value of a sub n term is greater than 1, guess what? Then the series diverges. Probably guess then part 3, if the limit as n goes to infinity of the nth root of the absolute value of the a sub n equals 1, then the test is inconclusive. very similar wording, right? These are said usually obvious which ones to use that on. It's the ones that kind of need the nth root there to simplify it down. Yeah, the problem, I guess, on this one is you've got n, and then you got to the nth power. And so, yeah, that's a real good example for the root test. Because what you're doing is you're taking the nth root. Well, you take the nth root of that, and you knock it down quite a bit, something more you can handle. So, yeah, this one's definitely root test way to go. And so on the root test, you're looking at the limit as n goes to infinity. It's not a ratio, it's just the nth root of the absolute value of a sub n term. Well, this is the a sub n. We always call it, so that's the limit as n goes to infinity. So it's the nth root of 3 over 4n nth power. Well, what this takes advantage of is that inverse nature of roots and exponents. Yeah, you got the nth root of an nth power. That just wipes out the nth root and the nth power, doesn't it? And so you have the limit as n goes to infinity of 3 over 4n, which is a fairly simple limit. You got 3 over infinity, that's 0, which is less than 1. So by the root test, you've got our series 3 over 4n to the nth is absolutely convergent. Okay? So yeah, you've got those expressions to the nth power. I guess they may not be quite so obvious in some of them, but a lot of them it is. All right, so let's take a look at this one. Series is 2n over n minus 1 to the nth. Now, what you might see on this one is we make an adjustment here because n can't be 1, so start at n equal 2, but that really doesn't affect anything that we're doing other than changing the first term out there. Okay. But again, you got that nth power of a pretty big expression inside there, so root test is the way to go here, I think, as long as it doesn't equal 1 anyway. So we got n goes to infinity, the nth root of a sub n, absolute value. So we do the nth root of a sub n is just that 2n over n minus 1 to the nth. Nth root in the nth power. So I've got the limit as n goes to infinity. But now it's just 2n over n minus 1. That's the nice thing about using this test for these. Yeah, fairly simple one. Just divide top and bottom by n. Show me that. So the n goes to infinity. It'd be 2 over 1 minus 1 over n. That's 2 over 1 minus 0. That's 2. And that's greater than 1. Ratio and root test compared to 1. It's greater than 1. So it diverges. Okay? All right. Now this one kind of has a slight little wrinkle to it, so let me show you this one. root test. This one is -3 to the n plus 1 over n to the n. So maybe not quite as obvious that root test would be involved, but the n to the n is kind of a key thing to key in on there. Yeah, that one suggests, since you've got an n in the base and an n to the power, root test is a good one for that. Okay. So what we got here? So the limit here in infinity, the nth root of an absolute value of a sub n. Well, again, the absolute value hasn't really played a role here. I just kind of dropped it on those other ones. I forgot to really talk about it, but the terms are all positive here, so I just wound up dropping the absolute value, but it was because the terms are positive. But here, we've got an alternating, don't we? That's going to mean alternating series. And so when I we do step by step here, that's one thing that is taken care of with this root test. I'm doing the absolute value, and so I can take out that alternating and just make it a positive 3 to the n plus 1.